So hello, do you hear me?
Yes, we can hear you.
Yes.
Great. So let's start. This time we will jump a bit to another topic, which then will be followed up by Rudolf, but I think it will be 3 weeks from now because the next Friday and the Friday after that is the national holiday. So what we will now look at is word embeddings, and in the context of this course, it will be the interesting thing for us is, of course, multilingual word embeddings. But first of all, what is it about? So essentially, everything, whenever you hear embeddings, it means something about vector representation of not necessarily words. Sometimes there are embeddings for various other stuff, but they're vector representation in neural networks. But specifically for word embeddings, the original task or motivation was something that actually predates neural networks by maybe 25 years. Or not neural networks. Neural networks were around also 25 years ago, but the current hype of neural networks in NLP, that definitely is quite a new development. So the motivation that I'm talking about is that uh, words are behind most NLP models for various tasks, and words are sparse, meaning that there are many words that you will never see in your training data, and there are even more words that you will see, but you will not see them in all the possible contexts in which they can appear. And that's sometimes quite a big problem, uh, because you often need to see the context to infer some information from the word. So the motivation, as it was put years ago, before neural networks, first by the team around Peter Brown in IBM research and development, and later, because this became a classic, so you can find it in various intro NLP textbooks like Juravsky. Essentially, the motivation is that, let's say we want to see, we want to estimate the probability of the bigram to Shanghai. And we have never seen this bigram in the training data. So the probability just estimated by the counts would be 0. But we know it's not 0 because it is a valid bigram that is quite likely to appear. And we have observed bigrams to London and to Beijing and to Denver and maybe to various other cities. So we know that if there is a city name and the preposition to, it is something that is likely to occur. So, and we've also seen the word Shanghai. So it's not an unknown word. We know it exists. We just haven't seen it together with this preposition. So the question is, can we somehow figure out that Shanghai is in some sense similar to London and Beijing and Denver because it's a name of a city, and therefore it's likely to appear in this context as well? And the answer is yes. If we observe it frequently enough, then we will be able to find out that there are other contexts that are actually shared by all these city names. And as a derived from that, we will deduce that in this particular context, it is quite possible that Shanghai will occur as well. So there was some, that's just the motivation, but the solution that was proposed in that year 1992 was what later became known as the Brown clustering. And Clustering means that you partition the space of the all possible words into clusters. There's a fixed number of clusters, but you fix it yourself, so you decide how many clusters you want to have. And you essentially do it iteratively. So you start by each word having its own class, and then you repeatedly merge two clusters into one. So you have to select cleverly which two clusters are close enough to be merged together. And you do it as long as you want to until you have the desired number of classes. So obviously, if you do it for too long, then you will end up with just one cluster and it will not help you at all. But the idea here is that if you can find out that London and Beijing and Shanghai and Denver all belong to the same cluster, then it will be possible to treat all the words in the cluster as one word. So instead of looking at the individual counts of London and Denver and Beijing, you will look at the uh, sum of all the occurrences of all these words inside a cluster. So we will treat it as if these were instances of one word. So now the question is how to find out that two clusters are good candidates for merging. And the idea here again is relatively simple. Um, if the words inside the two clusters are similar enough, then in the task that we have in the estimation of probability of bigrams, uh, the mutual information will uh, of those clusters will be low enough. So in other words, mutual information is how much does the event A decrease entropy of event B. That's the like wording of the formal definition. So entropy tells you how difficult for a particular probability distribution, how difficult it is to estimate to predict a particular event. And the event might be like at position I, there will be word Shanghai. And uh, if you have two events, like you have observed the previous word of the bigram and you want to predict the next word based on the previous word that you know, then these are events A and B. And so you're asking how, if you see the word B, how much will it tell? So sorry, it's here. Probability of A given B. So if you've seen the word B, how much will tell, reveal about the probability of the word A? And these are not individual probabilities of individual words, but this is the entropy of the whole distribution. So how much will seeing anything at the position I minus 1 will tell you about the position I. And mutual entropy is mutual, so you can really look at the word types. So it's you're not looking at individual positions in the corpus, but instead you are looking at all possible occurrences of one particular word and how much will tell you about the other word that you are observing. So you can look at it as like likelihoods of two word types. And then the only switch that we will do for the clustering task is that instead of asking about individual word types, we will ask about occurrences of any word type that's in the current cluster A and current cluster B. So when we apply this, and this is something you actually don't have to implement unless you want to do an exercise, because it has been around for such a long time that you just Google Brown clustering and you will find an implementation that you can download and use. So that's what I did. And besides that, there's also that paper about it. So in the paper, you will find some examples of clusters. So these examples from English, they are taken directly from the paper. So that's what they found. You could run it yourself on some English data. You will end up with something somewhat different, but hopefully not too different, depending on the data that you used. So there are some striking similarities. So you can see that Friday, Monday, Thursday, Wednesday all end up in one cluster because obviously they are used in a specific way in English. But also weekends and Sundays, and if the cluster is larger, then you will find some less prototypical members of that class. Quite often, the part of speech category will be honored in the clusters. But again, it depends on how large the clusters are and how diverse the dataset is. So June, March, that's also obvious, the months names, and then people, guys, folks, fellows, and so on. But also unfortunates and CEOs. I think this was done on some of the Wall Street Journal data as well. So some financial news were inside. And then great, big, vast, sudden, these are adjectives. And here are some proper nouns or proper noun-like adjectives, and John, George, James, and so on. There should be some verbs as well. But there's some pronouns down here. If I'm not mistaken, there are no verbs in this particular excerpt from that, but definitely there would be some somewhere. So here's another example. For those of you who understand Czech, this is really this is something I did, but using their software. So so I just downloaded the implementation and ran it over the Czech PDT data, and again, there are some striking similarities in some of the clusters, but not necessarily for all the words that you see here. So for instance, this second cluster here, for me, it's not very obvious what the meaning of the cluster should be. Obviously, some of the words are quite frequent. Even milionu is probably frequent because it's PDT, again, is newswire text. But there are others that are better. So most of the year numbers seem to be in the cluster number 1, even though there are some other words as well. But there, for instance, there are some personal pronouns here. Namu, mi, hoim. There are some modal and auxiliary verbs. So auxiliaries budou, bude are here. Měl, měla, mělo, měli, měli. There are various forms of the same verb here together with some other similar verbs. By, bychom, aby, the conditional particles seem to have a cluster of their own because they are not similar enough to anything else, and so on. So this is an example of what it does. And essentially you can see that it is some sort of estimation of similarity, at least for some of the words. So those that are frequent enough so that their similarity can demonstrate in the way they are used. And that's the main clue for this approach and for word embeddings as well. If the word has been observed frequently enough in a similar context, that's what will define that it is considered similar to the other word. So it can be similar semantically, but it can also be similar in its grammatical behavior, like is it a noun, and even is it a particular gender or number, because those will behave somewhat differently. Now, let's look at neural networks. The idea behind is still the same, but we are now a couple of decades later on the time scale. So now language modeling is still around, but as anything else, it's now typically done using neural networks. And the input to neural network, when you speak about words, typically the input would be something like an index vector or one hot vector. So you have a large vocabulary, the list of the words that you know, and you can, so let's say we have 10,000 words, and we can represent each word as a large vector. So there will be 10,000 numbers, 10,000 positions or dimensions, and at each of those positions there will be 0. Only one of them will have 1 as the value, and that will point to the position which represents the particular word in the vocabulary. So this way of representing a word obviously wastes a lot of space. So in the neural network, the first thing to do is to create some embedding, so to map the index vector into a vector that has a lower number of dimensions, a fixed number of dimensions also, because the vocabulary for each experiment might be slightly different, but you will decide that you want to have, say, 300 dimensions. That's your embedding size, and but those vectors will have a non-zero value typically at every position, and they will be somehow computed automatically, so you cannot say what the particular position actually means, but their properties will be that similar words again will have similar vectors, and we will look into this a few moments later. So the goal was the same. The setting is slightly different. If we look at the literature, probably one of the early attempts to do language modeling, at least what I found, to do language modeling using neural networks was Benjo and others, which was described as early as 2003. But apparently this model of Benjo was not tractable enough, so it took some more time to find out how to actually implement it so that it works. And at the same time, obviously the available computational power increased as well. So the hardware that was available in 2003 would not be able to deal with later work to back, but in 2012 the situation was already different. So then the main paper behind, or the one that sparked the interest in word embeddings was probably this one by Tomáš Mikolov from Brno and other people, but this was, I think, I don't know if it was a Google paper or Facebook paper. Tomáš Mikolov later was in Facebook. And that was the first in a long and large body of literature about word embeddings. And the main idea behind how they did it is called skipgram, and that means that you have a word in the middle of a larger window. So you look at a group of neighboring words, and you ask what is the probability that within that window around word x you will find a particular word y, and you try to model to train the neural networks such a way that it will learn the probability of these words and it will be able to predict it. So now I have some uh, stolen images to show you or to illustrate how this is supposed to work. So uh, there is always an input layer for a neural network. There is an output layer. So since we are now going to predict the probabilities of words that appear in the neighborhood of one particular word, so the input vector will be the input word. And as I said initially, this is a large vector of the same size as the vocabulary is. So if we have 10,000 words in the vocabulary, there will be 10,000 positions, and exactly one of those positions will be one. Then we have hidden layer of the neural network, which are the uh, neurons that represent each of the word differently, and we will look at it in the next slide. And then there is the output layer, which is the classifier. So here we have 10,000 neurons, 10,000 nodes for each of the possible words that could be in the neighborhood. And for each of them, we will have some set of weights that when pushed through the softmax classifier will give us an estimate of the probability of that word. So this is the probability that the word abandon is in the vicinity of the current word. And this is the the probability of the word ability and able and blah 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 up to the last word in the vocabulary, which in this example is zone. Well, it could be something else. So the hidden layer is also called embedding layer or embedding matrix. And matrix because it's 300 neurons. 300 is again that's an arbitrary number. So 300 is one of the commonly selected ones, but you could decide that you want 100, or you could decide that you want to have 500, and you could experiment with that and see whether it gives your task a better result or not. And then each of those 300 neurons has its own set of weights for each input word. So that's a huge matrix actually, because you have 300 neurons times 10,000 words. So for in each of the cells of this matrix, you have a weight for a particular word in that particular neuron. So if you have now the input word, it will activate its own weight in each of the neurons. So it will activate 300 weights, and all the other weights for the other words, other input words, will be ignored for this particular step. So you can look at it also as a large one-hot vector of 10,000 dimensions being multiplied by this embedding matrix, 10,000 times 300 dimensions. And the result of the multiplication will be the 300 weights for the particular word. So that's the embedding vector for the word. So as long as we know what the embedding weights should be, which we don't know before we train it, but let's now assume that we know it, that will be the representation of the word in the neural network. And that is something that if your neural network is not just for computing the embeddings, but for doing something more sophisticated like tagging or parsing, you would now go on with this embedding vector, and that would represent your word in the task of tagging. But that's not the topic that we want to cover today. So then our task is the simplest one. It's really just predict the output probability. So to say for every possible other word, or even this word as well, whether it is likely and how likely it is to appear in the vicinity of the input word. So the output layer has to have these 10,000 neurons for every possible output word or every possible predicted word. Again, each of those neurons has a vector of 300 weights. And we will now multiply our word embedding vector with the weight vector, normalize it using softmax, and as long as the neural network has been trained properly, the number that we will get will be the probability of the word y in the surrounding window. So here is yet another illustration that tries to illustrate what happens here. Let's say we have the word vector for the input word ants, and it's already the embedding vector. It's not the input one hot vector. So it has 300 features. And we have the output weights for car. So this is again 300 features, but you have to imagine it as oriented along the other axis, because you're multiplying the weights of this word, the word car, with the embedding features of the word ants. And what you get, you have to run it through softmax so that you normalize the numbers that you have here so that it looks like probabilities. It sums up to 1, and it's all of the words, all of the numbers are between 0 and 1, which is done by this ugly formula. So we don't have to do it really, because softmax is already has been implemented. And what we get is the probability. So all of this is still about just using the neural network if it has been trained already. And now the question is, how do we train it? So essentially you take, in every step, in every training step, you take a word X from the corpus. In the training corpus, you know what is in the neighborhood. So then you randomly pick a word Y from the window around X. again, the size of the window is something that you have to configure yourself. So typically it will be something like 7 words, or not too large a number. So you have X and Y. You know that Y was there. The input is the one hot vector for X, obviously, as if we were predicting the word Y in the vicinity of X. And then the output is actually, again, one hot vector for Y. So what we are saying here, or pretending here, is that instead of a probability distribution that will tell us there is like a 0.05 probability that there will be the word car, and 0.06 probability that there will be the word, I don't know, bus, and so on and so forth. We know that we have seen the word Y, and we pretend that it's the only possibility, at least in this step, the only word that can ever appear in the window. So we will say that the probability of the word Y is 1, and the probability of every other word is 0. And then we will compare this large vector with the actual output of the neural network, given the current weights in the neural network. And in the beginning, the weights can be initialized randomly. It doesn't matter, because this is a training procedure that is supposed to converge to the better, more fitting weights than anything that you started with. So then you compare them, you find out there's some level of error, and then this is something that I'm not going to explain in detail, mainly because I don't understand it enough myself. So you would have to go to the Milan Strakas classes to get more grasp of it. But essentially, there's a loss function, so you see how much you failed to predict the word correctly. Then you do all these derivatives and gradient descent and backpropagation, and you end up with updated weights in the network. And then you do it again and again. You look at the next word, you look at the next window around that word, you again pick a random word Y, and you try to predict it. And as you see, you can go even in multiple rounds around the whole corpus, because every time you will probably select another word to predict. And at some point, you will decide that you have learned enough, and that your network will not improve anymore, because it's already predicting as well as it can. So that's the training. You have now trained the language model that tries to predict the actual occurrence of other words in the surroundings. But now you can actually collect the embedding, so the hidden layer from the neural network, the embedding layer. So you will now have a representation, vector representation for each input word. And those are the 300 weights, or a vector of 300 dimensions, or you can call them features. That's also what people sometimes say. They are features in a sense, but as I said, you cannot say that feature number 275 encodes a gender or encodes whether the word is animate. Nothing like that. Those are abstract features that cannot be easily explained in human language. But still, they characterize the word somehow, and still, because they have been trained to predict what the context of the word will be if in real corpus. That also means that words that appear in similar contexts will have similar vectors. So that's actually what makes this approach similar to what Brown clustering does. But here it is a bit more interesting, because you can actually compute similarity of vectors. So you can say how much similar they are, and more interestingly, for a given vector, you can find the n most similar other words in the vocabulary. So then you will find out that the most similar words are like those that you would find in the same cluster in Brown clustering, but you can also use various vector algebraic operations, like you can subtract one vector from the other and add another one, and if you believe that they have some semantic properties or syntactic properties that the subtraction should capture, then you will see it. And I'm pretty sure Ruda has some examples. You will see them later in the practical part. So then the question is how you compute similarity of two vectors, and the thing that people normally do is the cosine similarity. So here's the formula. Again, I'm not going to prove every detail of that, but essentially it means that if the vectors have the same angle, so if there were just 2 or 3 dimensions, you could imagine that in the normal 2-dimensional or 3-dimensional space, but there are 300 dimensions. So you can still compute something like an abstract angle between the vectors, and you disregard the magnitude of the vectors. So you only look at the angle, and if they are orthogonal, then the similarity is 0. While if they have the same orientation, same direction, then the similarity is 1. So they are identical essentially, even though their magnitude may not be the same. So that's what makes some sense of the actual numbers in the vectors, even though you cannot say whether number 7 at position 8 means something concrete. You can still compare the numbers across the vectors of individual words. And by the way, you are not even guaranteed that you will always get the same numbers for the same word. It heavily depends on first on the initialization, random initializations of your neural network, and second, it depends on the data that you use. So if 2 people train 2 vector models for check, but on slightly different data, or even just with slightly different initialization of their neural networks, they will get completely different vectors in absolute terms, but still they should observe similar mutual relations between individual word types. Now, all of that was not multilingual. That was just for a single language. But as you could observe, the clusters and embeddings, in some sense, do what we also did with delexicalization, like partial delexicalization. You remove some of the lexical information, but not all of it. You just reduce it so that it's tractable, so that you don't have too many words and you have higher chance of observing each of them. It is unsupervised, so you don't need any annotation. You just need large amount of text because they only rely on the context. But the problem is that they will not work across languages because, as I said, if you run it for Czech and English, you will get some. If you run it twice for Czech, you will get different numbers. So obviously, if you run it for Czech and English, you will get different numbers that don't mean anything if you port them to the other language. So you cannot say that the English word dog is similar to the Czech word pes just because they mean the same thing, because they will never, or very unlikely, will a Czech word appear surrounded by English words or vice versa. And that holds for Brown clustering as well. So here's again one example from Brown clusters. Now I have run it on a concatenation of Czech and English data. It is actually a parallel data set from UDE, so it's not a large data set, it's just 1,000 sentences, but those are perfectly parallel. But the Brown clustering didn't know anything about the parallelism, so it just got first a large body of English, then a large body of Czech, and then it had to say something about how similar the words are. So it's not surprising that most of the Czech words ended up in their own clusters, and most of the English words ended up in their own clusters. And it is very rare that a Czech word, appears in the cluster that's otherwise English, like here. By the way, the purple ones are words that I believe could be regarded Czech as well as English, because like proper names, they will not be translated. And then there are some examples like on could be a Czech word and it could be an English word as well. but those are rare. So as we can see down here, there is a mixed cluster with rather typically function words, something that's very frequent, but these are not typical. Most of the time you will see a single language cluster. So we would want to do something about this. And if you do the clustering, the embeddings, you will see a similar problem. So people wanted to actually find out how to map vector spaces between different languages onto each other. And again, one of the pioneering papers in this area is Tomáš Mikolov and colleagues from 2013. And this diagram is taken from that paper. And the idea is quite simple again, even though it may not be as simple to actually implement it. The idea is that if you take the vector space that was trained for English and then the second vector space that was trained for Spanish, the positions of the words in the space will be different, but the mutual angles, positions, if you try to go from one word to another, those vectors should be similar. So in other words, the relation between cuatro and uno in Spanish should be very similar to the relation between 4 and 1 in English. And similarly, these are numbers. So down here, there are some animals. So a horse and cow should be in similar relation as caballo and vaca in Spanish. And this is a projection for from their model they trained with their neural networks. So it's probably projected to 2 dimensions, but it's probably from real data. So you can see that it's not exactly the same dimension, same relation, like caballo and vaca here appear to be closer to each other than horse and cow. But in general, the distribution of these words still seems to match somehow the same pattern. So the idea is, let's try to find a transformation of one of the vector spaces, let's say the English one, such that a small set of words for which we know the translation, so let's say for these 5 numbers and these 5 animals, will be mapped onto their Spanish translations. So these are our fixed point in the English space. These are our fixed points in the Spanish space. We know the mapping between them, and we will try to transform one of the vector spaces so that the corresponding red points will end up as close as possible to the corresponding blue points. Obviously, it will not be perfect because you never can find a transformation that will satisfy them all, but you will try to get the average best mapping as possible. So I think actually what I said for the picture was most of what is needed to know that. You need a small bilingual dictionary, and the transformation that you try to find out is essentially rotation and scaling. So you can multiply the coordinates in some dimensions by some weights, and you can find some rotation. So all this can be done using a transformation matrix, and the question is how to find the transformation matrix that will satisfy the mappings that you have in your bilingual dictionary. And the answer here is, once again, let's try a neural network that will learn how to find the matrix. So again, without any implementation details, it's again some training. So you know the answers for these 10 words and their translations, and you want the weights in the matrix to be as close as possible to yielding the actual answer that you know is correct for these words. And then you believe that once it has been trained, the answer for all the other words that you did not disclose will be good as well. And these are examples from their paper. So they found out that for Spanish emociones, they got emotions among the sort of translations. So these are not the translations actually. This is you transform the Spanish vector space to the English one, then you have the joint vector space, because now you believe that the transformed Spanish can be really merged with the English vector space, because it has been transformed correctly. And so you can look for the most similar English words, the closest vectors to the vector that describes Spanish emociones. And among the English ones, the closest one was emotions, which is a correct answer, and emotion with singular was the second closest vector, and feelings, and then so on. There, it could be endless, so you could have other more distant vectors as well. Protegida, protected, was among the three most probable ones, even though not the winner. And Imperio yielded something that is not considered correct answer, because correct would be empire. By the way, if you haven't noticed it yet, all these models are about modeling the word type. So you look at a particular word from the dictionary without the context of the particular sentence. So if you have something like an ambiguous word like bank, which could mean the financial institution, or I don't know, the banks of a river, then maybe the sentence would tell you which of the meanings is correct, and then you would end up with a different vector if you could take the context into account. But this model doesn't take it into account. So if you have an ambiguous word, you need to end up with a vector that somehow characterizes all of its possible senses. So they also did some experiments with English to Czech, but this is a somewhat different table. It does not show you the most probable three most probable or most similar words in the target vector space. Instead, it takes the absolute most probable as the they say translation of English, and then they compare it with some sort of dictionary that they had. And now, when I was looking at this slide before this today's class started, I wasn't sure anymore what kind of dictionary it should have been, because some of the translations look a bit strange, but probably they were taken from some larger texts as well, because to translate English did as Czech ano, meaning yes, I can imagine a sentence where this will be correct, but I wouldn't put that into a dictionary. So anyway, it just illustrates that again, if the word is ambiguous, you cannot always get the best translation, because the vector of the ambiguous word will be somewhere in the middle of the meanings, while in the source language maybe only one of those meanings will apply to the source word. Finally, here is some other possibility. There are many possibilities, at least what people tried for multilingual word embeddings. You could also try to model the skipgram across word alignment. So if you have not just two large monolingual texts, but if you have a parallel text where you see the word alignment, then you can try various tricks to your model, and you can pretend that you are switching from English to Czech and back at random points. And this will simulate that the neural network will see the English context of Czech words and vice versa. So if we have this is again a sentence pair from the parallel UD tree bank, and so there is English above and Czech below, and these are the alignments which I think either I just put them there manually, or because they are not part of the parallel tree bank. But anyway, this is how the alignment could look like. So now, if you look at the word výdaje, which means spending in English, you could also say that výdaje, the context of výdaje is the new in English and is fueled in English. And you could play with this. So you could then say that when you go across the when you iterate over the sentence, at random points you will jump over this blue line and then go on the other side and jump back and so on. And you can see there is different context for different check words, but sometimes it may be a bit more tricky because some of the alignments go diagonally to words that are more farther apart. But still, you can do something like this for all the words. And then this is one of the possible random transitions over the sentence, over the pair of sentences. So that's almost all I had. The last thing that I wanted to mention is another paper that was published about multilingual word embeddings, and that's a completely unsupervised method by Chen and Cardi from 2 years ago. And essentially, the idea here is that you try to train a network that will tell you for a vector what vector space it is likely to come from. So you will create embeddings for multiple languages. You will do that monolingually. You will just, you have, let's say, 10 languages, and for each of them you have a large monolingual corpus. So you will train the embeddings. And then you will try to train a network that will tell you that this vector is likely to come from the English embeddings. And the second most likely is the Spanish embeddings, and then it drops. So something like that. And you can train the network because you have the training data. You know which language, which vector space the vector comes from. And then you try to train a converter from other languages to something like an interlingual vector space. So the multilingual vector space that is for all the languages together. And for that converter, initially we don't know what to do there, how to make the vectors similar. But so that will be training this converter will be another neural network. But you will try to make the converter so good that if you take the converted vector, the classifier network will no longer be able to recognize which vector space it comes from. So in other words, you will try to make all the languages look the same for the classifier. And the idea here is that if you manage to do that, then you will actually have a good converter, and you will really have a common vector space where all the languages are mapped approximately to the positions where the words should be. And obviously there will be a lot of noise here, so it will not work perfectly, but it did yield some results. So they then tried to add a second pseudo-supervised step, where they would start with this adversarial training of the converter network, and then after they got some approximate alignment using this network, they will trust the translations of some high frequency words. So that will yield something like the bilingual small dictionary, which we would have used for the bilingual vector space transformation. And then we can use this bilingual dictionary and align each pair of languages more tightly. But this will be only for the two languages again, while that first part was for many languages at once. That's it. So unless there are questions now, I think we can move to the practical part. Okay, Rudolf?
Okay, so it seems there are no questions. So let's move to the practical. So can you hear me?
Yes.
Great. That's better than last time. Okay. So I hope you can see my screen now.
Yes.
Fine. So today the topic of the practicals, unsurprisingly, is word embeddings. First, monolingual word embeddings, then bilingual word embeddings. And I've realized that it takes a lot of time to download the models, to run the models, because they are quite large. So I will be showing what to do, but it's probably not reasonable to wait for everything to happen, because like downloading the model can take like 5 to 10 minutes and so on. I will be just showing that here, but I've already downloaded the models and so on. So first, monolingual word embeddings. There is the Vertaweg tool, which is kind of the classic, but actually it's recommended to use a newer version, which is called FastText, and which has some advantages, but anyway, like Vertaweg is not maintained anymore. So for this lab, we will be working with FastText. It's quite easy to download and install it. Then with the models, it's harder because the models are large. But at least to see the installation, that's easy. As it says here, you just clone something from a Git repository, and then you make it, and you get a directory with some files. Most importantly, you get the FastText binary. I will now move this elsewhere. So, sorry. Yes. So, by itself, it doesn't do much. If you run it, it just tells you that it has a lot of options to use, but you need some models or some data to actually do anything useful with it. So one thing is that you can use your own text corpus to train a model, and this actually is kind of an optional part of the lab. Like if you want to, you can actually try that, because it's useful to be able to do that. So that's the optional part here. So you can, for example, download some Wikipedia texts, and there is Wikipedia text for many languages available just for download. And you can then run FastText to train the word embeddings for that. But mostly you don't have to do this, because a good thing about FastText is that it comes with models already trained for 157 languages. And so let's look at that. And this is mostly enough, but if you're working with a weird language, then you have to train your own model, but the website just says how to do it. And for every language, there are two options: a binary model and a text model. Now, I'll show how both of them look, but generally the binary model is if you want to directly use it with a FastText tool. The text model is if you're interested in the vectors themselves and you want to use them with something else. So let's see what we have. So I have downloaded models for English and for Czech. So let's first look at the English vectors, what it really looks like, these magical vectors. So surprisingly, they really look like a set of numbers. So this is the text format, the .vec file. It's a Vertaweg format. This is the number of words in the file and the number of the dimension of the embedding. So how many real numbers you get for each word. And the format of each line is that there is the word at the beginning, so a comma, for example, or the, and then there is the vector. And the words are ordered by their frequency. So the most frequent words are at the top. So if the file is too large for some processing, you can just take, I don't know, first 10,000 lines from the file, and you will have embeddings for the first 10,000 most frequent words. And okay, so it's not much fun to look at it this way, but it's good to understand what we're really working at. So this is what the model computes for you. And then there is the binary format, which is not very good for viewing, but it's kind of compressed, and it's what the fastText tool can work with. So let's get back to the text format again. And the idea of word embeddings is that the embeddings for similar words are similar. So let's try to do this. So I will grab the first occurrence of the word dog, and I have some terrible vector here. I will do the same with the word dogs, and I have another terrible vector here. And yeah, if you're into that, then you can try comparing the dimensions one by one, and you should see that they are kind of similar. So this is obviously not the way we usually do it, but it's educative to see that it really works this way. So if I would just take the first 10 dimensions for dog and for dogs, so we could see that, yeah, some numbers probably similar. It should be more similar than if you take a very different word, such as, I don't know, a television. So in this case, the numbers should be different. Probably they are. So it's not, of course, much fun to just look at the numbers. So you could easily just compute the cosine similarity of these and see how similar these actually are. And luckily, the tool already comes with capabilities like that. So I already have it running somewhere, but let's try to run it so that we see. So if I run the tool, so it says there are some options of what you can do with it. And actually the first things are the ones that are usually not used at all. This is if you want to train a predicting model which predicts something for words. So for example, a part of speech tagger. Then the next options, these are if you want to train your own model on text. So you provide it with some plain text and you get a word-to-vec model or word embeddings model. Then this one is to get some word embeddings for words or for sentences. And then these two are the ones that we are actually going to use. So NN for nearest neighbors and analogies for analogies. So let's see what this really means. So I run the tool with the NN option, and it tells me how to use it. So fastText NN, then a downloaded model in the binary format, and K to say how many nearest words I want to see. So I will take the English binary model, and I will just say, yeah, 10 is a good default. And I run it. And now it loads the model into RAM, and it takes some time. So I'll switch to my already running model, and let's see what happens. So once it starts, it asks for a query word. And so if I say my query word is dog, so it looks for the words that are most similar to the word dog. So you get dogs or puppy or some other information. If you look for, I don't know, something more specific, tiger. So you learn that, yeah, tigers are similar, but you get some other animals like lions or leopards. And if I don't know, look for January, yeah, it's similar to months. Now, the good thing is that unlike brown clusters, this is kind of soft similarity. So for each of these words, you get a number, a score, which tells you how similar these words actually are. So all months are kind of similar, but there is more. So actually, you even see that the winter months are more similar to January than the autumn months, and still the spring and summer months are even less similar. So it can do even these kind of soft differences. Or if I look for Wednesday, I should get some other days of the week, like Tuesday and Thursday. Again, the neighboring days are the most similar, but then the rest of days are there as well. So that's one of the tasks it can do. And it's also good to have an idea how these things look like. So I'll be showing this visualization tool, which is called Projector. And so what it does is that it takes the word embeddings. I don't know if this is visible well through the Zoom, so you can also click it yourself. So it takes some word embeddings, and you can use some pre-trained word embeddings with it, or you can load your own embedding file if it's in the right format. And it does some kind of visualization of the vectors. So obviously the problem is that the vectors are 300 dimension or 200 dimensional in this case, and it just puts them into 3 dimensions. So obviously it's just some kind of approximation, and you can choose the method to use to display these 200 dimensions into these 3 dimensions. So the default is principal component analysis. So it just takes the 3 most interesting directions, and you can use some other visualizations as well. And the nice thing is that we now really see all the words that are in the dictionary somewhere. So if we zoom in sufficiently, so we can see some words that are similar to each other. So I'm now finding some parts of the Bible, for example, in this region. And I don't know, Jedi. Okay. So again, it's hard to see anything meaningful this way, but you can even search for words on the right. So if I search for the word, I wanted a dog. Okay. So for dog, so it finds words that contain the string dog. And so you can see there is dog, dogs, and dogma. And what we would like to see is what we do see. So dog and dogs seem to be more similar than dogma to these two. Obviously, if you look for cat, that's hard because there is a lot of words that contain the substring. You can also switch on regular expressions. So I would just want to see the word cat. And I'm seeing the word cat itself, and then I'm seeing again the similar thing that I would see in the terminal. So the most similar words by distance. So the number of neighbors I want to see, it's, I don't know, 100. I can choose cosine distance or another distance. Then I see this one word, and then the cloud of the most similar words to it. I can just look for words ending day, and you would see that, yeah, Monday, Sunday, Saturday are in one region, and other words like day, today, or holiday, they're somewhere else. So these are all different ways of visualizing word embeddings it's like none of the ways is perfect. So all of them are just to give you an idea. But it's better than nothing. So so I want to show the other task as well that the fast text tool can do by itself. So I want to see, okay, so the nearest things to a hospital are some typos. Okay, it's a big model, so there is even a lot of typos in the corpus. Let's try, I don't know, school. Yeah, again, but kindergarten, okay, that's a good thing, or teacher. Yeah, educator, that's a good synonym of a teacher. Now, the next thing the model can do is so-called analogies. So this is doing basically some mathematics with words and word meanings. And you run it the same way. You say fast text, analogies, and the binary model. And yeah, I have one example to see. So for example, we take the word teacher, which does have some meaning, and we kind of subtract the meaning of a school from the teacher. So we should get something like a teacher, but without a school. And then we add another word, and we can add the word hospital. So that's the original word A, you subtract school and you add hospital. So this kind of means that we replace the schoolness of the teacher by some kind of hospitalness. And let's see what happens, if something happens. Take some time, but yeah. So we're getting some words like, okay, so a teacher in a school is something like a nurse in a hospital, or a physician or a doctor in a hospital. These are nice words. A patient, well, this would be more like a student in a school, but yeah, it's kind of a similar thing. So that's one part of the magic of the word vectors, that if you just add or subtract the vectors themselves, so it's somehow similar to adding or subtracting the meaning. So the most famous example is, of course, this one. So we have to try it. So we take a queen and we remove the womanness and replace it by manness. So we get the king. So that's good. But once you install the tool and download a model for English or for any other of the languages, then you can play with it and see what happens. So I don't know if we take it's lowercase probably. If we take Putin and remove his Russianness and replace it by Germany-ness, so we're getting Hitler actually as the second result. So it's interesting. Or I don't know, if you take Russia but remove vodka and replace it with beer, for example, then you're getting some beer countries. Or when you replace it with wine, then we're getting some wine countries. So this is kind of mostly for fun. So if you train your own embeddings, this mostly tells you whether you've trained the embeddings correctly. So if yes, then things like that should work there. But yeah, the word similarity, of course, that's pretty useful. So the word similarity itself, you can, for example, use it for word synonymy. Or then if you have a bilingual projection of the words, then of course you can use it for projecting word embedding, so having similar words across languages. So I don't know if you have a difficult word. So it can tell you something about the word. So okay, we maybe don't know what's endocrinology, but we know that okay, it's similar to some other logies, so we can guess what it could be. And the model is really large, so you can try whatever you like, and you will get some information about everything. So that was the monolingual word embeddings themselves. Probably after the class, feel free to install the tool, to download a model for some of the languages, and then to play with it to see how it really works. And if you want to, you can also try training your own model. And now let's move to the bilingual embeddings themselves. So this will actually be the homework assignment. So there is a link to one of the tools for creating bilingual embeddings. So there are multiple, of course, and it's still an area of active research. So you might get new tools in future as well. So this is one of the tools that's, well, we can say it's already old because it's from 2018. The good thing is that it's quite easy to use. You just download it and use it, and there is quite nice documentation for it. So I recommend working with that one, but if you want, you can work with another tool as well. So it just works with any pre-trained embeddings from Word2Vec or FastText or whatever, and it can map the embeddings between the two languages in 4 different setups. So if you do have some parallel data, it can do a supervised mapping. So it means it takes a dictionary and it just maps the corresponding words to each other. But if you don't have parallel data, it can still do something. So either the identical matching, which expects like things like, I don't know, numbers and punctuation should still match across languages. Or if the languages are really weird, you can still do the unsupervised matching, which just looks at the spaces of word embeddings and checks whether they have a similar space. Try to match the spaces, try to conflate it a bit. So it's all the same tool, but as much data as you have, just try to provide the data and it will make a better mapping. If you use the supervised mapping, then it's pretty fast. The other ones are pretty slow, so it can take a few hours, but it's all written here. And you can evaluate it, of course, yourself. And there are some papers which use some specific settings and so on. But that's fine. So the good thing is that if you do have word embeddings for some languages, so you can map them to each other just by downloading and running this tool. And what it does is that you give it, so you can give it the dictionary if you have one, and then the source language and target language embeddings, and it produces 2 new embedding files, which is source mapped and target mapped. So these are, again, 2 separate files of word embeddings for the source language and for the target language. But the vectors are different. So now in these mapped files, the vectors for similar words should be similar. I have the tool somewhere. I just have to find it. No. Okay. Where did I put it? Okay. So, the tool itself contains several scripts, and yeah. If I have here I tried check and English, and I tried mapping check and English vectors. So for this you need the text vectors, and let's again check how this worked. So I will grab for the vector for dog in English, and again just the beginning. And I will try to grab the corresponding word in Czech. So these are the mapped vectors for these words. And yeah, you kind of can see that they are kind of similar. Whereas if I tried to do the same with, now if I find the right path, with the original files, and now I need the Czech file. I only have the binary one. Okay. Don't know. I somehow have to have the Czech file as well, but I don't know where I put it. It's probably just up here. Yeah. Okay. Okay, so I'll show the English one below. So in the original files, so the vector for pes and the vector for dog in the two word embeddings files were quite different, because as Dan said, there is the random initialization and everything. So there is no guarantee that the two similar words should have similar vectors which are trained independently. But after mapping these through the VecMap tool, you get vectors that actually are pretty similar. So this can be used very nicely for cross-lingual experiments. And this will actually be your homework assignment. So let's get over that. So what's the idea? So the idea is to do, again, cross-lingual parsing, but now with bilingual word embeddings. So again, the idea is still the same. So let's take two languages, I don't know, English and Czech. And let's say we have data for English, but we don't have data for Czech. So we want to train a parser on English and then use it on Czech language. And the whole idea of this bilingual word embeddings approach is that we train word embeddings for both Czech and English, then map these two embeddings to a common space, and then we train the parser with English embeddings, but these mapped English embeddings, which means that if we then run it on Czech text, it can still work with Czech text as well. That's the idea, and if you already know how to do this, so you can do it yourself in any way you like. I'll just go over the bullets here. So that's the suggested approach that should get you there. So you choose a source language and target language. So I said Czech and English, but it's more meaningful to choose some target language which is really low resourced. So you can use some of the languages you used before, like Kazakh or anything else. And you need to get word embeddings for the two languages. So probably you can just download them from the FastTech website. And you will need the text format for this, because it's for the other tool. And now you run VecMap on these two word embedding files. So you can just use the identical unsupervised setting, which doesn't require any parallel data. So the identical just relies on some identical words in the two languages, like numbers. The unsupervised, it just relies on the shapes of the vector spaces, but you get better results if you actually use the supervised setting, where you provide a bilingual dictionary. And getting a bilingual dictionary is pretty easy. So we already worked with Pro data, we already worked with FastAlign to get word alignment. So you can just take the intersection word alignment and take the pairs of aligned words and say, yeah, this is my bilingual dictionary. So that's pretty easy to do actually. And that's already what I actually did somewhere here, I think, but I don't know where I have it. Don't know. Okay. Yes. So so if you have the intersection alignment, which looks something like that, then you can just extract a dictionary. You have to decide what to do with words that appear multiple times, but you can just leave them there, or you can just do the most frequent aligned pair. That's not really so important because it's just support dictionary. And so you can see my results are quite messy anyway. So you get a bilingual dictionary in this format, and you run the VecMap tool. So it produces 2 new embedding files, one for the source language, one for the target language. Now, what we still need to do is that we need to combine them into one file for UDPipe. So the idea is that we train UDPipe for just the parser, and UDPipe by itself computes its own monolingual word embeddings on the training data, which we don't want. So we want to specify that we already have, an embedding file. And this will be incorporated into the trained model. So this is a mapping from words to vectors that the model will use in training and as well when running it. So we need the embeddings to contain both the source language embeddings and the target language embeddings. The source language embeddings for training and the target language embeddings for testing. And we just rely on the fact that the similar words in source and target language will have similar embeddings in these mapped embeddings. So we basically, you can just concatenate the 2 files. So you have embeddings for Czech, embeddings for English, and you just concatenate the 2 files together. So you get bilingual embeddings. Ideally, you would do something a bit more clever, but not too much necessarily. So one thing is that, of course, each of the embedding files contains the first line, which is a header. So this should be there just once. That's pretty obvious, and it should contain the right number. So if you combine 100,000 embeddings for Czech and for English, so you should put there, it's actually 2,000 embeddings. And of course, the reason why the VecMap tools produce 2 separate files is that there are words that appear in both of the languages, which might or might not mean the same. So in this case, we probably want to remove one of the occurrences and just assume that they mean the same. Or if you wanted to be super careful, you would just do some special preprocessing, like prepend a special character to every English word, a different one to every Czech word, and then do the same preprocessing with the training data, with the testing data, so that you can have 2 vocabularies at once. But I think it's just sufficient to concatenate the 2 dictionaries. And once you have that, you're basically done. So you train the UDPipe just in the default lexicalized way. So without the tokenizer, without the tagger, we are just interested in the parser now. And you say that you already have an embedding file for the parser. So it uses that, it trains for the source language, and you can then apply this model to the target language, and it should work pretty well. Of course, the final step is to evaluate it. So you should see how it works on the target tree bank. and you should compare it to some meaningful alternatives from the previous task. So the lexicalized parser, projective parser, supervised parser, whatever you like, just to see if these bilingual embeddings really worked, if they brought something better, or if it's just as good as the lexicalized parsing. So that's the idea. So as Dan said, there are now 2 Fridays which are free. So I've set the deadline for the homework, the default one, so 10 days. But actually, if you need more time for that, then that's probably fine, because there will still be some time before the next class. So so try to go through the materials from the class at home. So try to use the FastText tool, try to download the models, try to see if it works. And just beware that if the models are large, then it takes a lot of time to download. It's several gigabytes often, and it takes a lot of memory to load the models actually. If you work with smaller languages, then it's actually easier. So the quality of the models is probably not so high, but already the Czech model is smaller than the English model, and then the Kazakh model will be even smaller. So that's a good way to start, so that you don't overload your computer right at the start. And otherwise, that's all from me. So if you have questions, so please ask, and otherwise we're done.
A very interesting lecture. Thank you.
Thanks. Okay, I can see no questions, no problems. So thank you for attending, and yeah, see you in 3 weeks actually. So of course, feel free to write an email if you need something and so on. And yeah, see you later.
Thank you. Bye-bye.
Bye.
Bye-bye.
Thank you. Bye.